Every black hole creates a new growing universe inside of the event horizon.
Nikodem Popławski is a genius. Although that word should be used with great humility, his concept that black holes create new universes was recognized by National Geographic and the journal Science as one of the top 10 most important ideas of the year.
So our universe has billions of black holes, and each black hole makes a new universe. So basically our universe makes billions babies.
The article describing black holes was one of the most frequently cited in the history of science news.
I try to connect those two things, which means Einstein-Cartan theory with space-time torsion and the idea that a new universe is formed in every black hole.
Morgan Freeman, in his famous Curiosity program, referred to him as the new Copernicus.
That matter after the bounce has to expand somewhere, so it expands into a new space. So it creates a new closed, growing universe. So we will never see what's on the other side of the black hole unless we go there.
Host of the conversation is Michael Wyrobkowski, is the European Research Director at Yale University, currently associated with the University of Pennsylvania.
Professor, I would like to start our conversation with a discussion of black holes. Specifically, I would like to ask you why reconciling black holes with the universe expansion is such a key to our understanding of the universe.
Yeah, black holes are very fascinating, and we know that they exist. The Nobel Prize was given like several years ago for confirming that black holes are a robust prediction of Einstein's general relativity, and this was done like 50 years ago with seminal works of Roger Penrose and Stephen Hawking. And black holes are very fascinating, but we still don't know what is inside them, because black holes are regions of space-time such that nothing can escape from the inside. And the boundary of the black hole is called the event horizon. So the standard general relativity predicts that when a star forms or when there's like a lot of matter at the center of a galaxy, then a black hole forms, and then the matter inside the black hole, and inside is defined within the event horizon, the matter contracts further until it reaches a gravitational singularity, which is a point or a ring, for the case of rotating black holes, where the curvature of space-time and density of matter are infinite. However, the infinity means that our understanding of physics, of nature, is incomplete, because infinities cannot be measured, and physics is experimental science. So if you cannot measure something, that means that it's not physics. So this problem was bugging me for years, and I wanted to explore if there is some alternative, how to remove gravitational singularity. And there is the old extension of general relativity. The oldest extension is called Einstein-Cartan theory of gravity, which says that energy and momentum of matter give curvature of space-time, and this is something that Einstein already said. But intrinsic angular momentum of matter, which is called spin, which is like of particles such as quarks or electrons, which are called fermions. Intrinsic spin of fermions creates torsion. Torsion is this another property of space-time, which Einstein assumed to be zero, and Cartan relaxed that condition and said, hey, let's assume that torsion can be whatever it wants to be. The field equations will decide. And then, according to Sciama and Kibble, who did more research on Cartan theory in the 60s, they found that intrinsic angular momentum or spin of matter creates torsion. And then in 1970s, researchers found that torsion manifests itself like a gravitational repulsion, which means when the matter wants to create a singularity in a black hole or at the Big Bang, the matter reaches extremely high densities, much bigger than nuclear density, and then torsion, which is negligible. Torsion is negligible usually. It's unnecessary to make torsion equal to zero like Einstein did, because torsion is almost zero everywhere. But at extremely high densities, torsion actually becomes very strong, and at those densities, torsion acts like gravitational repulsion and prevents the formation of singularity. So researchers already found out that universe with torsion did not have a Big Bang, which is a singular and density is infinite, but there was something before. There was something before the Big Bang, because if the Big Bang was not singular, then what was before? And of course, there's like a lot of theories, like we can think what's there. But when I learned Einstein-Cartan theory, then I learned also about some hypotheses like Hawking and Smolin had, that every black hole final singularity becomes initial singularity to a new universe. But then in the process, like laws of physics can change. So like things can be very random. But I try to connect those two things, which means Einstein-Cartan theory with space-time torsion and the idea that a new universe is formed in every black hole. I found that, and this is basically the relation, how the black holes related to the universe.
So if I understand you correctly, so say we are an observer flying in a spaceship, a little bit like Christopher Nolan's Interstellar, flying towards a black hole, we meet the event horizon. So if we go through the black hole that you mentioned, would we be going to another universe?
That's what I believe, because connecting Einstein-Cartan theory of gravity, which replaces singularity, with a bounce, which now we can call it a big bounce instead of Big Bang, then if singularity is avoided in a black hole and the matter bounces back and starts expanding, but that matter cannot leave the event horizon because the motion through the event horizon is like one-way trip. It's like one directional motion. So that matter after the bounce has to expand somewhere. So it expands into a new space. So it creates a new closed growing universe. So basically I believe that every black hole creates a new growing universe inside, or probably I should say instead of inside, on the other side of the event horizon.
I do wonder whether outside of the one-way trip that we'd be making through the black hole, we could learn something about that universe. Because say, can we use any of the characteristics of the universe that we are in correctly, say observable mass of the universe, to learn anything about the black hole that created our universe? And also, can we learn about what's on the other side, about the quote-unquote mother universe?
Yeah, so we will never know what is inside a black hole, because if we try to send someone to the black hole, then we will never see in our time, because time is relative. So time on Earth is not the same time as time on the spaceship which goes to the black hole. The time on the spaceship runs more slowly than our time, because gravity slows down time. This is the effect of gravity on time and space.
Just like in Interstellar,
yeah,
right?
In Interstellar. The main character became younger than his daughter because he spent like some time near the black hole, and it slowed down a lot of his time. So basically, we will never see that spaceship crossing the event horizon, because at the event horizon, the proper time, which is the name of the time on the spaceship which moves, with the spaceship, the time measured by the observers on the spaceship, we call this the proper time of the spaceship. Proper time of the spaceship is different than time on Earth, and actually when the spaceship crosses the event horizon, the ratio of proper time on the spaceship to our time reaches 0, which means time freezes and we cannot go beyond. We cannot extend. We cannot compare our time on Earth. If time on spaceship crossing black hole freezes to 0 relative to our time, that means we will never see the spaceship crossing the event horizon. So basically, from our perspective on Earth, the spaceship will cross the event horizon after infinite future, after infinite time, which means we will never see what is on the other side, because we will never see that spaceship crossing.
But would the observer in the spaceship learn anything about the other universe, or would it be torn apart?
That's a good question. So, and before I answer this, I want to say also that the same applies to a black hole which forms, because we can put the observer, so if you have the matter which star collapses to a black hole, we are going to put an observer at the surface of that star, and then in the proper time of the observer which collapses with the star will see that at some finite time event horizon forms and black hole forms. But people on Earth will never see that. People, by analogy with a spaceship, the people on Earth will see that the observer who was on the surface of collapsing star will reach the event horizon after infinite time, which means the star contracts to a black hole after infinite time, which means black hole never forms. From the perspective of on Earth, black holes don't exist yet. They are almost there. They are forming from our perspective outside after infinite time. But for the observers who are collapsing with the matter, the black hole is already there. Black hole forms. Now, we will never see from outside black hole, we will never learn what's on the other side, because from our perspective, the other side did not form yet. It will form after infinite time. So we will never see what's on the other side of the black hole unless we go there. Because even if we send someone, that person will never tell us, because we will never see that person going there.
So just a second. So the black hole forms from our perspective after infinite time. So would it mean also that another universe that's on the other side
forms after infinite time? Which means from our perspective, there is only one universe, our universe, and there's no black holes. All black holes and all the baby universes on the other side of those black holes form from our perspective after infinite time. In order to see if it's true or not, because you never know, maybe it's not correct. But if this hypothesis is correct, if we choose one black hole, we go there, we realize that actually we cross the event horizon in finite time. We may actually even participate in the formation of that event horizon. So I'm investigating this actually. But we go to we are in the new universe on the other side. We cannot go back. We cannot tell anyone, we cannot send any signals. We cannot tell anyone outside what we saw, which means they will never know, which is consistent with what I said, that we will never know. But when we are in the black hole, we forget about our universe. I mean, it's gone because we cannot go back. Now, the interior of the black hole or the other side is our new universe. This is now our universe, and this is the only universe, because in that universe, there may be other black holes which did not form yet from our perspective. So it is now our universe.
Almost seems like a fractal.
Yes, it is. It is. So our universe has billions of galaxies. the observed one, because we don't observe because there is a cosmological horizon, because they are parts of the universe which expand faster than the speed of light, so we will never see them. So we will never see the whole universe. So, but the observable universe has billions of galaxies, and as far as we know, almost all of them have supermassive black holes at the centers. Each galaxy has one supermassive black hole at its center, which means our universe has billions of black holes, and well, from our perspective, they are almost black holes. Now we know that they are black holes because you can tell if an object is a black hole or not if you measure radius and mass. Mass you can measure by measuring speeds of objects orbiting about. It's like a classical mechanics. And the radius you can measure, and there is something called Schwarzschild relation between mass and radius of the black hole. If you see the object whose radius and mass are in that relation or very, very close, then we know it is a black hole, almost. It will be a black hole. Or it is already in the proper time, but for us, it's almost there. So our universe has billions of black holes, and each black hole makes a new universe. So basically, our universe makes billions babies.
So on that
new
note,
universes.
So on that note, I do wonder, because say from our perspective, we know the mass of the black hole that's creating this baby universe, but it also, it also has we all know Hawking discovered the Hawking radiation. Does it have any effect whatsoever on the baby universe that's inside the Hawking radiation?
Oh, so actually, it is a radiation which is equivalent to Hawking radiation. Hawking radiation was about radiation of a black hole because virtual particles are created near the event horizon, and one of them goes inside, second does not, which means now they are not virtual anymore, now they're permanent. And the ones which don't go inside, they go outside, and it looks like a black hole is radiating. But of course, energy is conserved, so eventually black hole will be shrinking and evaporate. Now, in my hypothesis, if a black hole has a new universe on the other side, so that universe does not evaporate or vanish, what happens is the connection from our universe to new universe evaporates. So basically, thanks to Hawking radiation, the baby universe disconnects from the parent universe.
See.
And it's gone. It's basically the connection is gone, because the event horizon is basically Einstein-Rosen bridge, a wormhole which connects. So I believe that every black hole becomes a wormhole which connects our universe, the parent, so we are the parent, to the baby universe. And the Hawking radiation, two things. So one thing is that this connection will evaporate at some point. So from our perspective, we will see black hole disappearing, but the universe on the other side doesn't disappear. It is basically the connection from us to the baby universe disconnects. So the baby disconnects from the parent. Now, a second thing is that the analog of the Hawking radiation, which is the Zeldovich-Parker-Starobinsky radiation, it was basically something similar to Hawking radiation. It is basically a production of pairs of particle-antiparticle, but not near the event horizon, but at strong gravitational field which changes in time. And basically the same mechanism which explains Hawking radiation explains that radiation. And that radiation says that in the black hole, when big bounce happens instead of singularity, big bounce means very huge deceleration. Matter collapses very quickly, and then suddenly it stops and bounces back. So there's like you go from contraction to expansion. So there's it happens very quickly. So it is very huge acceleration. So gravitational field changes in time very, very quickly. According to the Hawking radiation applied there, we get huge mass production. So there is a lot of particles per mass, a lot of matter and antimatter particles and antiparticles are being produced, but unlike Hawking radiation, which is because one goes into the horizon, second doesn't go, both of them are still there. So basically, in the very quick time, there is a lot of new mass created, and that's why the universe on the other side of the black hole is much more massive than the original black hole which made the universe. So because of course our universe is much more massive than stars. So thanks to this pair production, the new growing universe on the other side of the event horizon can be much more massive and than the original parent black hole, and also can be much bigger, because the other side doesn't have to be the same size as the parent black hole. The other side of the black hole can be much bigger, and that's not inconsistent, because we cannot see that yet, because remember, from our perspective, the black hole never forms, which means the baby universe, which is much bigger than the black hole, never forms. But once we go to the black hole, we realize that the space we are in is much bigger than the entrance we went through.
I see. So it's a little bit like Chronicles of Narnia, when you open the door of a wardrobe, you go inside and you see...
Or Doctor Who.
Or Doctor Who, right.
That you enter the police box and you find yourself in the beautiful ship, which is much bigger than the door.
So I do have a question regarding energy. So, and because the universes, the baby universes never form. So, how does the transfer of energy or for that matter mass look like from our universe to the baby universe?
So, of course, when a black hole forms, it forms from the original mass, which is like in the star or at the center of galaxy, where you don't need squeeze matter too much, you just have a lot of it in big space, and black hole forms naturally. You can make black hole from water without squeezing it, but you have to have a lot of water. For example, if you imagine that you have the orbit of Jupiter, you make a sphere which is as big as orbit of Jupiter. If you fill that sphere with water, it will be a black hole instantly.
Wow.
Because big black holes, you don't need to squeeze, because such a huge sphere of water will already have the Schwarzschild relation between mass and radius. So, or from air even. You can make like a Neptune orbit, you can have a black hole made of air. So now small black holes, you have to squeeze them. That's why it's harder to make small black holes from stars, but from at the center of galaxies, it's very easy. So basically, we can, so in order to see what's on the other side, well, we have to go there. You have to go there because, as I said, the black holes don't form, and observers trying to get there, from our perspective, they will never get there. The time when they reach the event horizon, they cross it, is infinite. But once you go inside, then you could see the new universe. You cannot tell anyone what you found, because no information can be sent back, because nothing goes through the event horizon both ways, only one way. It's like a one-way ticket. And you can be in the new universe. Now this new universe may be old or young, it depends. So I don't know yet how to predict the age of the baby universe once you cross the event horizon, because we don't want to, let's say if we decide to leave our universe and go to the baby universe, we don't want to end up with a universe which is very young and hot. It would be very not good to live there. You want something which is cold, and when you have all stars already there, like sun, so they can produce energy, and you can have some energy and life. But now about the energy. So matter is being produced near the Big Bounce by the quantum production, and energy is conserved. This doesn't violate conservation of energy or momentum. Energy, momentum, and angular momentum, all those things are conserved. Mass is not conserved, but mass
doesn't have to be conserved.
Mass doesn't have to be conserved, because energy is not only equal to mc squared. Energy is not only mass, energy is also gravitational energy. And the thing is that energy of mass and motion is positive. Energy of gravity is negative, which means you can make mass out of nothing, provided that from zero you make another zero, but you make some new matter such that all gravitational energy of that matter, which is negative, cancels the positive energy of mass and motion, which means total energy is still zero. So you can make zero from zero, and that's how the Hawking radiation. And now Hawking radiation is different because energy is being lost, but only because some particles they split. But if you create pairs in the closed universe, I wrote an article like several years ago that I showed that the closed universe, I proved that energy is zero in the closed universe, which means in the closed universe you can make matter out of nothing, and energy is conserved, and you for free can do it.
Right, and it's because of gravity.
Yes. Now, you could also say, could those particles go back and annihilate themselves, basically go back from zero to zero, but from matter to not matter? And the thing is, they will not, because there is also something called second law of thermodynamics, and some processes which go both ways are more probable one way than the other. And second law of thermodynamics, the increase of entropy, actually, entropy increases if you produce new mass from nothing. So this is favorable.
I wanted to come back to the idea of torsion that you mentioned. I wonder whether this specifically could be the missing piece between general relativity and quantum mechanics. Would you say so?
I believe so. I believe so because so I researched that torsion eliminates gravitational singularities, and also the dynamics of the new baby universe after a big bounce behaves like cosmic inflation. So torsion can do both avoidance of singularities and inflation, and explain where we came from, because assuming that if every black hole makes a new universe, then by extension our universe was born in a black hole existing in some universe which is parent to our universe, and we have like billions of siblings because that universe made other black holes with other new universes. But in addition to this, yes, I believe that torsion is something which could be the missing piece in quantum mechanics, because quantum mechanics is linear theory, and linear theory is that if you have two solutions and if you add them, then you have another solution. And because of that, you have quantum superposition, which is related to linearity of quantum mechanics, that electrons can exist at multiple positions at the same time. And when you try to measure where it really is, it basically randomly chooses one location and it disappears in all other locations. And that's weird, that's strange, I didn't like it. It's a standard Copenhagen interpretation of quantum mechanics. Of course, a lot of quantum physicists say, well, let's not worry about this, let's not worry about the collapse, because you can never observe that. You can only observe outcome, which means you measure the particle where it is, but quantum mechanics beautifully calculates probabilities. If you have billions of electrons, and you have probability, then you can actually, and you measure all of them, you will find they randomly choose those locations, but the distribution agrees with probabilistic calculations. So quantum mechanics statistically gives you good numbers. Now for one electron it's random, can be here or there, but you cannot apply probability for one electron because you'll measure it there. There's no probability, but you have like billions, identical ones, then you can see that, oh, some of them are here, some of them are there, you can do probability. Now, because of torsion actually violates linearity of quantum mechanics, because Dirac equation, which is relativistic quantum mechanics equation, is cubic in the wave function. There is one little tiny term which is nonlinear, which means Schrödinger equation, which is non-relativistic limit, also is nonlinear. So quantum mechanics is nonlinear, which means we cannot have superposition, which means we cannot have electrons being here and there at the same time, because it was possible only if quantum mechanics were linear. So, in my opinion, torsion will favor one interpretation of quantum mechanics in which it's called pilot wave interpretation of quantum mechanics, or de Broglie bomb interpretation, which initially was interesting, but then most physicists like Bohr, Heisenberg, they were like strongly opposing the interpretation. It became like a standard interpretation, the Copenhagen. Then you have electrons everywhere, and you have collapse of the wave function that no one understands, and no one cares. But the Broglie-Bohm pilot wave interpretation of quantum mechanics says that electrons are localized. They only exist at one point, and they are being guided by the pilot waves, which satisfy Dirac or Schrödinger equation. So this interpretation gives the same numerical predictions. However, in the presence of torsion, well, there is a little more, but experiments cannot be done yet because we don't have such huge densities or micro scales.
I would like to look back at your theories and specifically torsion, the centerpiece really. Assume that you have infinite resources. Really, all the physics labs out there are under your control. What would it take to have evidence for torsion? What experiment would you need to conduct to have something tangible? Okay, torsion exists, therefore all the other things follow.
So torsion is significant at extremely high densities, which are like approximately 10 to the power of 45 kilograms per meter cube. And neutron stars, which are the densest objects in the universe, have only 10 to the power 17, which means effects of torsion regarding the density are very negligible on Earth or solar system, or even like in stars and in our galaxy. So in order to prove that torsion exists astronomically, we have to only probe the regions where densities are very big, which means either inside black holes or at the Big Bang. We cannot go inside a black hole, and even if we go and find if torsion is there or not, we cannot tell to Earth what we found. So this is excluded, which means the Big Bang. Now, because if every black hole creates a new universe, then our universe was born in a black hole. So we are the other side of the black hole which formed our universe. And from our perspective, we see the other side of the black hole as white hole. So if we ever discover in our universe a white hole, which looks like a black hole, has the same geometry of space-time around it, but the only difference is that the matter does not go in, it goes out. So if we ever discover one, and it has to be only one, two white holes would be too much, and I don't know how it's possible. If we ever discover one and only one white hole in our universe, it will be kind of indirect proof that something is good about this, that universe makes the black hole makes a new universe. However, this is very difficult. But if our universe was born in a black hole, then the expansion of the universe immediately after Big Bounce, which replaced the singular Big Bang because torsion got rid of singularity, the dynamics of the universe immediately after the Big Bounce, knowing how it expands, and inflation, and torsion, by the way, also predicts inflation. So maybe more constraints on inflation could possibly favor my theory that how torsion makes inflation. So if we know that, so knowing the earliest the earliest moments of the universe expansion could tell us whether torsion, which gives very specific dynamics, is correct or not. Now, we cannot see the earliest moments of the universe because the oldest light we can see was formed 370,000 years after the Big Bang, or Big Bounce in my theory. Because before that, light was stuck. The universe was not transparent for light, so light was stuck with the matter. So we cannot use light. We cannot see the earliest moments of the universe. But we could use gravitational waves or neutrinos, because they can freely go through the hot matter. So I would say that the future is in the gravitational waves astrophysics, which is very new, because gravitational waves were detected for the first time, 10 years ago? Well, indirectly in 1974, they were proved to exist by the Hulse-Taylor double pulsar. People found that if the gravitational wave exists, they carry away the energy according to Einstein's equations, such that the orbital period of those two pulsars gets smaller and smaller according to the observation. So this was indirect proof, but now we know that they exist thanks to Kip Thorne and the experimental detection by LIGO. So we know, so gravitational waves is a very new research, and also neutrino. We know neutrinos exist, but we still don't use them yet to do cosmology, or it is very new. I think the astronomers already started. So I believe that astronomy of neutrinos and gravitational waves can tell us how universe expanded after the Big Bounce and could prove torsion. But this is only astronomical part of torsion. My biggest hope is, and you said that if I have resources and I want to do it right now, is use particle physics. Because in presence of torsion, Dirac equation becomes nonlinear. And also I wrote a paper in 2010 showing that because of torsion, elementary particles cannot be points. So what is electron? We believe electron is a point, but we can probe it with some technological accuracies. We know, as far as we know, electron is bigger than electron is smaller than 10 to the minus 22 meters. That's a very small number. Planck's scale is 10 to the minus 35, so that's still huge. But if torsion exists, I calculated that electron will not be a point. It will be some kind of flare structure which has size 10 to the minus 27 meters. Planck's scale is 10 to the minus 35, so that's much bigger than Planck's scale. So we don't have to go to like quantum gravity or some 10 to the minus 27. So that's only 5 orders of magnitude below what we are capable now. So maybe in 50 years we can reach the 10 to the minus 27 meter scale, and if we discover that something is crazy about electrons at that scale, this would prove torsion, because torsion actually gives this number, because other models, they also have some theories of extended particles, but there'll be different numbers. So particle
different
physics,
scales, right?
Yes, different scales. So particle physics is affected by torsion through this extended size of elementary particles. And secondly, quantum field theory. In the presence of torsion, momentum becomes non-commutative because of translations are non-commutative, and because of that, integrals in Feynman integrals, which calculate probability of certain things in quantum field theory in particle physics, they get replaced by convergent sums. So infinities are removed, but also there are tiny corrections from torsion to those probabilities in quantum field theory. They are very small, but I believe that at some point they could be detected. So I think that quantum field theory, like scattering cross-sections of different processes or lifetime of decays of some particles, they may be affected by torsion, and possibly this could be some direct proof. So I would say particle physics. So I mentioned neutrinos and gravitational waves to probe the earliest moments of the universe, but to be more on Earth, not to be waiting for things in the universe, just do it in some laboratory. I would say particle physics to check how torsion affects quantum mechanics and quantum field theory.
Right. So Professor, just to conclude our conversation, first and foremost, thank you so much. Another thing is that I can only second Morgan Freeman's quote from one of his cosmological documentaries, saying that you're a second Copernicus. And if I may say, not only because of the fact that you were born in the same city as Copernicus in Poland some 5 centuries ago, you're clearly opening to us new vastness of new universes on the other side of black holes, even if we may not reach them ourselves here on Earth. So thank you so much.
Thank you very much. And also I want to finish with the statement that sometimes we may have to wait a long time to verify something. Albert Einstein predicted gravitational waves in 1916. 1974, they were indirectly shown to exist. And in 2000, like what, 8 or 18, they were detected. So sometimes it takes 100 years or Higgs boson, 50 years. So sometimes it takes decades. So maybe torsion has to wait maybe 50 years. Hopefully I'll be alive to see if it's detected. I'll be very happy.
Hopefully it will be detected much sooner. Thank you so much, Professor.
Thank you.